Feed 1,000,000 tokens into a standard language model, and you force it to hold every single word and every possible relationship between those words in active memory simultaneously. Eventually, the hardware breaks under the computational weight. This is the core bottleneck of test time scaling. Standard attention mechanisms have a quadratic complexity. If you double the context length, the computational cost quadruples. Ultra-long contexts quickly become economically prohibitive. DeepSeek-V4 Pro is a 1.6 trillion parameter model that activates 49 billion parameters per token, yet it operates at a 1,000,000 token context natively. This chart shows the single token inference flops as sequence length increases. Notice the widening gap between the gray dotted line, the previous generation, and the solid blue lines of V4. At 1,000,000 tokens, V4 requires only 27% of the inference flops used by DeepSeek V3.2. The memory savings are even more significant. This is the accumulated key value cache footprint. At 1024K tokens, V4 operates with a cache 9.5 times smaller than its predecessor. DeepSeek reached this level of efficiency through architectural and systems engineering. This performance is driven by a 3-tier co-design: hybrid attention mechanisms, mathematical depth constraints, and wave-based kernel fusion. To understand how LLM scaling evolves from here, we have to look past raw parameter counts and deconstruct how V4 manages the geometry of memory and communication. For long-horizon agent tasks, the primary challenge is the bloat of the key value, or KV cache. This is the first problem DeepSeek targeted. The first intervention is Compressed Sparse Attention, or CSA. CSA compresses the KV caches along the sequence dimension. It uses compression weights and positional biases to consolidate M entries into a single, denser block. Navigating this requires the Lightning indexer. A query token casts a low-rank FP4 projection across the sequence, calculating index scores for each block to locate relevant information. The model performs top-K selection, routing data through only the highest-scoring compressed entries, while ignoring the rest. The second branch is Heavily Compressed Attention, or HCA. HCA uses an aggressive compression rate to consolidate a much larger number of entries. Unlike CSA, it skips the sparse routing of the indexer to prioritize massive memory reduction. This heavy compression creates a vulnerability. The model cannot easily access the fine-grained data in its own immediate neighborhood. To preserve these local dependencies, V4 adds a third branch, Sliding Window Attention. This keeps the uncompressed data for the most recent tokens. The model interleaves these three mechanisms, CSA, HCA, and sliding window, layer by layer. By combining precise routing with aggressive compression, DeepSeek decoupled sequence length from memory exhaustion. While attention handles the horizontal sequence length, the model's vertical depth presents a different problem. Standard hyperconnections often become unstable when scaled across 61 layers. Standard hyperconnections expand the width of the residual stream into parallel lanes without increasing the hidden size of processing layers. Stacking these unconstrained mappings deeply leads to numerical instability. The data waveforms spike, eventually causing gradient explosion. DeepSeek addressed this with Manifold Constrained Hyperconnections, or MHC. The model restricts the residual mapping matrix to a specific manifold, the Birkhoff polytope. This effectively cages the data waveforms inside a rigid geometric boundary. The Sinhorn-Knopp algorithm forces this constraint through 20 iterations of normalization, snapping the waveforms into uniform alignment. This constraint ensures the matrix's spectral norm is strictly bounded by 1. The transformation becomes mathematically non-expansive, which prevents signal drift. Bounding the input and output transformations in this way prevents the signal from canceling itself out over extreme depths. By caging the residual stream inside strict geometry, V4 maintains perfect signal fidelity from layer 1 to layer 61, providing the mathematical stability required for hyperconnections. Performance also depends on how the model handles the physical interconnect between GPUs. In mixture of experts models, communication is often the bottleneck. Standard expert parallelism relies on all-to-all communication, which creates latency that leaves GPUs sitting idle while they wait for data from other nodes. DeepSeek observed that massive interconnect bandwidth is unnecessary if the computation volume is high enough relative to the communication volume. Communication latency can be hidden if scheduled beneath compute-bound operations. Their solution is fine-grained expert parallelism, powered by a custom tile-laying mega-kernel. The system divides experts into microwaves. As wave 1 finishes dispatch, it begins computation, while wave 2 starts communication simultaneously. This creates a steady-state pipeline where computation, token transfer, and result sending all occur concurrently. This results in a theoretical 1.92 times speedup on inference and RL rollouts without any changes to the physical hardware. DeepSeek increased efficiency simply by refusing to let a streaming multiprocessor sit idle. CSA and HCA solve the memory bloat, MHCA stabilizes the deep routing, and custom mega-kernels hide the communication latency. Optimization strategies like FP4 quantization and the muon optimizer push this efficiency further. The muon optimizer uses hybrid Newton-Schulze iterations to ensure rapid convergence for the MOE modules. These systems-level efficiencies expand what the model can do during the post-training phase. DeepSeek moved away from traditional scalar-based rewards for hard-to-verify tasks. Instead, they use generative reward models, where the model uses its own internal logic to evaluate reasoning trajectories. This is followed by a multi-teacher on-policy distillation pipeline, where a unified student model learns from the output of specialized experts. The payoff of this hyper-efficient pipeline is the Think Max mode. The 1 million token context allows Think Max to carry complete reasoning histories across long-horizon agent workflows without flushing the cache. While previous models often had to rebuild their problem-solving state from scratch on every turn, DeepSeek-V4 retains the full chain of thought. DeepSeek-V4 demonstrates that performance at the million token scale is a product of the co-design of algorithms, systems, and geometry.